So today we'll study the modeling of turbine and governor. So last class we discussed uh, the exciter modeling completely. We devoted a full class on exciter modeling. How already you have seen how we derived the exciter modeling, exciter voltage regulator and rate feedback, and PSSC actually we did not discuss because it is easy to understand PSSC when we will talk about small signal stability. So during that time only we will see the PSSC design. Okay. Okay, so we'll start now. So last class we discussed this. This was the last slide in the last class. The transfer function block diagram of the exciter, right? This is your voltage regulator transfer function. Then the output, of course, is voltage VR, and this shows the exciter transfer function, right? This is feedback constant, and this is your saturation function. Okay, this is a nonlinear function. This is saturation function. Now, your rate feedback transfer function is this kf by tf by 1 plus stf, and another constant kf by tf is added, and this vf is actually compared with v reference along with vt. So this is your block diagram of the exciter along with the voltage regulator and rate feedback. Okay, now we'll talk about the model of the turbine. So what is turbine? Everybody knew very well. I think you have been studying in your BTech, MTech every time. So turbine is the component which actually helps to run the machine, synchronous generator, right? The rotor. So this is the prime mover, we can say, and it can be a diesel generator, gas turbine, or hydro turbine or steam turbine, whatever we want, it can be. So prime mover provides the mechanical power required as input to the synchronous machine. So it provides the mechanical power, in fact, to rotate the rotor of the synchronous machine at synchronous speed. So let us talk about the modeling of hydro turbine first. Then we'll talk about the modeling of the steam turbine, which is in fact very important because most of the large generators in most of the countries, the large generators are consisting of hydro and thermal, that is steam turbines. And of course, there are many other turbines, gas turbine, there are also renewable based wind turbine system, many other turbines are there. But we'll focus here on hydro turbine modeling and steam turbine modeling. So let us first see the hydro turbine. So this is a typical figure of a hydropower station. So those belong to the generally specifically from Odisha or northeastern states or Jammu and Kashmir. They are very well acquainted with, or West Bengal, they're acquainted with these hydro turbines because many times during BTech also they visit these plants. So this is a hydro power plant situated on a river, like on a river where we make the dams. This is a dam, right? Sometimes also in the waterfalls also we do these hydro plant stations, like making some reservoir, right? So this also can be possible, and where the waterfall is there and we are making a reservoir and dam, it is also possible. So here we have the dam which helps to reserve the water. Very huge volume of water is being reserved. If you see the reservoir, it looks like a sea, very huge. If you have visited or not, I don't know, but I have seen many reservoirs, water reservoirs before the power plant, like in Odisha, we have seen Hirakud. Jagya, you have seen Hirakud? Yeah?
I have, I have not gone there.
Okay. So Hirakud, there is a very large power station we have in Odisha. But this is like
Then
this reservoir is very
near
huge.
Sample barrage, one OHBC means hydropower plant was there. I have seen there.
Okay, okay. Okay, so in the main components in a hydropower plant is this reservoir, water reservoir, and then this penstock we are seeing here. This is your penstock, and this penstock is connected to the turbine. Here is your turbine. Okay, this is your turbine, and the turbine, of course, connected through the same shaft with the generator. Generally, the hydro generators are vertical in nature. They are installed in vertical because the turbines have to run in a vertical, horizontal manner. So therefore, it is placed or it is installed in a vertical position. We can see here, right? And as you seen again, the water will be passed to the tail race where the water again it is passed in the river and it goes for agricultural purpose. Right. Now the generator output is connected to the grid through the generating transformer. Right. Of course, it is a step-up transformer. Now water here we have here sluice gate. Sluice gate is actually here in the reservoir itself. It controls the water flow. And here we have valve also, right? The valve actually helps to inject the water because the water is injected to the turbine with a high pressure. So therefore, these valves are used to create sometime high pressure, sometime low pressure, based on the requirement. Okay. So this is controlled by the governor mechanism. Okay. So we'll see about that. And these are the important components: generator, turbine, penstock, these valves, right? Sluice gate and here the valve at the turbine. Okay. So now if we'll see here, this H from the turbine to the reservoir. This H indicates the head of the water reservoir. Okay. And this is a very important parameter, H head. And next is your U. U is the water flow rate. Okay, it is the velocity of the water or water flow rate, we can say, to the turbine. And another quantity G. G is your valve uh, opening. Okay, that is based on some power. Okay. So now the velocity of water can be expressed as this. This is a empirical empirical formula, empirical equation derived through experiment. U is equal to KUG square root H. H is your head. G is your uh, valve opening, and Ku is your constant, proportionality constant. Okay. Now, if there is a small change in the velocity of water, it can be expressed as sum of linear changes in the gate position and the head as this. So this equation, if we'll linearize with a small change of velocity, right? So with a small change of velocity, I can write delta U equal to the delta G of U evaluated at G naught H naught into delta G plus then delta H of U evaluated at G naught H naught into delta H, right? G naught and H naught, they are the initial, or we can say base values or some equilibrium operating points, right? Then your delta U, I can write just by taking the derivative of this expression, partial derivative, I will find Ku square root H naught delta G plus Ku to Ku divided by 2 into H naught square root G naught delta H. So we know that U naught, that is the waste flow, is equal to Ku G naught H naught. And now, if I normalize this equation by dividing U naught in both the sides, so I'll divide U naught here, delta U by U naught, and other part, the expression of the U naught, I can divide. So after dividing and cancelling each other, I can find here, this will become delta U bar, which is in the normalized form, therefore I am writing delta U bar equal to half of delta H bar plus delta G bar. Okay, so this H bar, G bar, and U bar, they are the normalized quantities. Okay, now the turbine mechanical power is proportional to the product of pressure and flow. Okay, and hence with proportionality constant Kp, I can write this. So Pm, that is the mechanical power exerted by this water. Okay, it will be Kph into U. U is your flow rate and H is your head of the water reservoir, right? Now again, a small change in Pm can be expressed in normalized form with initial condition as given above, HO and EO. So I can write this as delta Pm is equal to delta H plus delta U bar. Delta H bar plus delta U bar. That if I a little bit manipulate, just I'll substitute point, it will become 1.5 delta H. I'll substitute here from delta U to here. So then it will become 1.5 delta H plus delta G bar, right? Then from Newton's second law, force into mass, force equal to mass into acceleration, I can write another equation, that is rho LA d by dt of delta U. Okay, this is your acceleration because change of rate of change of the flow rate is acceleration. That will be equal to minus A rho Ag delta H. So rho LA is the mass because rho is your mass density, L is your length of the penstock, and A is your cross-sectional area. So it will be equal to minus of A rho Ag into delta H. Okay, so Ag is your, I can say that here, this rho Ag is the, Ag is your force. Okay, so to normalize the equation, I will now divide both sides by A rho Ag HO U. So if I divide this both the side, I will have now in the normalized form, the equation will be L U naught divided by Ag H naught, that is d by dt of delta U bar, right, equal to minus of delta H bar. Okay. So now if we'll evaluate LUO divided by AgHO naught, that is in the unit of second. So I can represent this as a time constant. Okay. So I can represent that as time constant. So now that will, the equation will become TW. It will become TW d by dt of delta U bar equal to minus delta H bar, right? So this will be the equation. Now TW is your, as a second, as its unit, which can be verified from this equation. It is called as water starting time, and it is the time required for a head HO to accelerate the water to a velocity of U naught. In Laplace domain, I will write, if I write this equation now, it will become TW S times S of delta US, U bar S, equal to minus delta HS. So we know this equation, right? And from this equation, I can again write delta HS, right? So delta H bar S will be twice of delta U bar S minus delta G bar S. Just by taking the Laplace transform of this equation, I can write this equation. Now substituting this delta H bar S here in this equation, I will find delta U bar S will be 2 by 2 plus STW delta G bar S. A little bit, if I will manipulate, it will become 1 by 1 plus half of STW delta G bar S. Now, we know your delta PM equation, that is already we have derived this, that is delta H bar plus delta U bar equal to 1.5 delta H bar plus delta G bar. And again, if I'll substitute this delta H bar here in this equation, now it will become delta PM bar will become thrice, 3 times delta U bar minus twice of delta G bar. So now from this equation, I can write delta U bar will be equal to 1 by 3 times delta PM bar plus twice of delta G bar. So now if I'll substitute this delta U here in this equation, I will find the equation of delta PM in terms of delta G. So my objective is to find delta PM in terms of delta G. Delta PM is the mechanical power of the turbine, and this is your uh, delta G is your valve power. Okay. Now I wanted to find it, the transfer function between delta PM and delta G. So now I can find it is as 1 minus STW by 1 plus half of STW. Now, this model is a linear model and hence is only valid for slow, gradual, small changes and not for the sudden large changes. This is a linear model. So in time domain, I can write this equation particularly. I can write it as just this is a transfer function model. I will convert it to time domain, so it will become TW into dy dt of delta PM is equal to twice of minus delta PM plus delta G minus TW dy dt of delta G. Okay. Also, since the model is valid for perturbations around an operating point, we can write the actual parameters as this. So if I want to express this equation in terms of actual parameter, so I can write PM is equal to PMO, PM0 plus delta PM, and similarly G I can write GO plus delta G. So now if I substitute this delta PM, delta G in this equation, now it will become TW dy dt of PM equal to minus of PM plus G minus TW dy dt of G. Since the synchronous machine model is represented in per unit, the turbine model also should be presented in per units. To do this, we can divide both sides of equation by base MVA or the rating of the synchronous machine. So if we divide this base MVA, both the side, also it can be noted that in per unit, power and torque are same. So therefore, I can write this as in terms of torque. So it will become TW d by dt of Tm will be equal to twice of, instead of Pm, I can write Tm minus Tm plus G per unit minus TW d by dt of G per unit. They are in per unit now, right? After dividing the base MVA both the side, right? Now this is the model for your hydro turbine. Okay. Now we'll talk about the steam turbine. So if we'll see the steam turbine, it looks like this, because hydro turbine has a single stage turbine, only one stage. And here the steam turbine can have many stages, multiple stages of turbine. So therefore, steam turbine is very high speed turbines. They're around 3000. They rotate at around 3000 RPM, 2000 RPM, right? So therefore, we can see here that this there are three stages of turbine we can see here. One is your high pressure turbine, intermediate pressure turbine, and low pressure turbine. And in case of low pressure turbine, we can have also multiple stages. But when we model for the simplistic point of view, we'll only consider two stages: high pressure, low pressure, or high pressure, intermediate pressure. We can directly only consider high pressure and low pressure also, right? Now, from the turbine here, the input is a steam, high pressure steam with high temperature. And the steam, in fact, comes from the boiler. The boiler produces the steam, high temperature and high pressure steam, and it is being stored in the steam chest. In the steam chest, it is very huge chest where the steam is being stored, and from the steam chest, it is actually injected to the high pressure turbine first through the valve mechanism. There are some valves are there, that valve opens and it is injected to the high pressure turbine. And then the outlet or the output of the high pressure turbine again will be steam, right? But here the steam will have little change of pressure and temperature. It will gradually decreasing, right? Now again it passed through the reheater to again reheat the steam, and again the output of the reheater is either passed through the intermediate turbine or it can be directly passed through the low pressure turbine. Okay, so now we'll see the model. So the steam generating system consists of a boiler to generate steam chest with a valve to store the steam and release it into the turbine as shown in this figure. The steam from the steam chest initially enters a high pressure turbine through the steam valve nozzle at high temperature and pressure with a high velocity, and this gets converted into rotational kinetic energy through the blades connected to the turbine shaft. Now, as in case of hydro turbine, the position of the steam valve is proportional to the mechanical power output of the turbine. Okay. So these steam turbines are actually horizontally installed in contrast to the hydro turbines. Hydro turbines are vertically installed, but the steam turbines are horizontally installed, right? Part of the input power gets converted into mechanical power at the high pressure turbine shaft, and the steam then enters the reheater where the temperature and pressure of the steam are increased, and then again this reheated steam is forced into a low pressure or a series of intermediate and low pressure turbines. Okay, so now we'll see. So each of these turbines convert the steam into rotational energy through their blades connected to the shaft. The connection can be tandem connected, that is all high pressure, intermediate pressure, low pressure turbine, and the generator are on the same shaft as is shown in figure, or cross connected, that is there maybe two shafts cross connected with same steam input valve and two generators connected to each shaft respectively. So the steam chest with a valve and high pressure turbine can be modeled as a linear fast flow system. So we can see this is the figure, right? This is your steam chest, and here the power when the power is steam valve position. So according to the steam valve position, and the steam is being entered right here to the high pressure turbine, right? Now, if I write the transfer function of the steam chest along with the high pressure turbine, here actually PCH is the power exerted by the steam from the steam chest, right? When the high pressure steam is being passed through the high pressure turbine, the input power is PCH. Okay. Now, the input power is delta PSV. Based on the valve opening, this actually delta PS increases, delta PCH increases or decreases, right? So therefore, I can write this as, if we'll write a linear function, linear transfer function with time constant TCH, I can write TCH d by dt of delta PCH equal to minus delta PCH plus delta PSV, right? So delta PSV is your output. Sorry, delta PCH is your output, delta PSV is your input, right? Okay. So now I can write it as yes, delta PSV by delta PCH. So, okay, so this is your linear equation, right? Now, if I write the equation for the reheater, I can write again for the reheater, I can write TRH d by dt of delta PRH. So delta PRH is the power associated with the steam at the output of the reheater equal to minus delta PRH plus input is your output of the this delta PCH and the remaining power in the delta PCH, right? Because when the PCH is and the steam actually passed through the high pressure turbine, let us say the KHP PCH is the power which is being used. This fraction of power is being used to the kinetic energy of the shaft. Now the remaining power in the steam will be 1 minus KHP into PCH, right? Or you can say delta PCH for an incremental change, right? So 1 minus KHP into delta PCH. That is what here it is substituted, right? So now the input to the reheater is the steam having this much of power. That is fraction of the delta PCH, that is 1 minus KHP into delta PCH, right? This is your input to the reheater. This is your output, right? Now I can write this as transfer function. If I write delta PRH is by delta PCH is, so a transfer function will be, how much it will be? It will be 1 minus KHP divided by 1 plus S times TRH. Okay, so this will be your transfer function, right? Okay, so similarly here, if I write the transfer function, it will be delta PCH S by delta PVSPS will be equal to how much? It will be 1 by 1 plus TCH STCH, right? Okay. So this is what it will be. Simple transfer function, right? Linear transfer function. So now we have two equations because we are considering here two-stage turbine. So we'll have only two equations, and these are the two equations now, right? So now if we'll write the total power delta Tm because of this first high pressure turbine and the second intermediate turbine or low pressure turbine, whatever stage we are considering, it doesn't matter. So now the total power of the turbine that I can write in terms of torque also, because in per unit power and torque they're same. Delta Tm I can write in per unit, that is equal to delta Pm. So this, therefore I can write delta Tm is equal to delta PRH, which is the output power of the intermediate turbine. Okay, or sorry, output power of the reheater, which is used in the intermediate or low pressure turbine to run the turbine, right? And this portion is KHP delta PCH is the input to the high pressure turbine, or which is being used, actually used in high pressure turbine to run the turbine, right? High pressure turbine to run the shaft, right? So therefore, I can add these two terms, that is delta Tm will be equal to delta PRH plus KHP delta PCH, right? So now eliminating delta PRH, we can represent the dynamics of steam turbine system, right? So because we want to eliminate this delta PRH, okay. So now I can write the delta PCH, right? And sorry, delta PM or delta TM and delta PCH. Okay. So now if I eliminate, I'll substitute delta PRH here in this equation, and then I can write the equation of delta PCH and sorry delta PSB and delta TM, right? Because delta PSB is your valve power, valve opening, the power actually used for valve opening, right? Or you can say valve power, right? Simply. That means the power of in the steam, power associated with the steam at the valve point, that is delta delta PSB, right? So I want to write the equation of delta Tm as a function of delta PSB. Now I need to eliminate delta PRH and delta CH. So very simple, I can eliminate and I can write this as delta PCH term will be there. Okay. So it will be there. Now your TRH into d by dt of delta Tm will be equal to minus delta Tm plus 1 minus KHP TRH by TCH into delta PCH plus KHB TRH by TCH into delta PSB. Right? So now we wrote the delta Tm as a function of delta PSB. Right? So now this is your final equation, final differential equation of the turbine. Right? And in association with this, we have another equation of the steam chest, like TCH dy dt of delta PCH equal to minus delta PCH plus delta PSB. So these two equations are associated with your steam turbine transfer function or steam turbine differential equation, right? So in case the reheater dynamics are not considered, let us say the reheater dynamics is not considered, then I can write TRH is equal to 0. And hence the dynamic equation can be written as this. Right? And when I substitute this TRH equal to 0, this term will become 0, this term will become 0, only delta PCH will remain, right? This term will become 0. So therefore it will become minus delta M plus delta PCH will be equal to 0. That means when the reheater dynamics is not there, your delta Tm is directly equal to delta PCH. Okay. And similarly, your differential equation will become this, right? TCH dy dt of delta Tm will be equal to minus delta Tm plus PS, right? Okay. So because instead of delta PCH, I can substitute delta Tm. So here, therefore, I can write TCH into dy dt of delta Tm will be equal to minus delta Tm plus delta PSB. And now substituting, if I want to write this equation in terms of actual variable, I can substitute Tm is equal to Tmo plus delta Tm, PCH equal to delta PCHO, PCHO plus delta PCH. Similarly, PSB will be equal to PSBO plus delta PSB. Now substituting this, I can find these two equations in terms of actual parameter, that is TRH will be equal to dy dt of Tm equal to minus Tm plus 1 minus KHB TRH by TCH into PCH plus KHB into TRH by TCH into PSB. Now the second equation will become TCH into dy dt of PCH equal to minus PCH plus PSB. So now these two equations are your dynamic equation of turbine, steam turbine. Okay. So this shows the dynamic equation of steam turbine consisting of a high pressure turbine and another low pressure turbine, which is connected through the reheater, right? Now this is all about your uh, modeling of the turbine. Now we'll see the modeling of the turbine governor. Okay, so this is the classical system. We can see this is the most classical system used very long back, and this we can model very nicely. And this is a, we can say this is a hydraulic turbine system where the hydraulic governor system, sorry, turbine governor system, where actually the high pressure oil and flywheel mechanism is used to control the speed of the turbine. Okay, so how it is, we'll see. We can see here we have two bar links are there, right? Here and here. The two bars connected at a hinge C, right? And this hinge is free to move, right? This is not a fixed hinge. Okay. And now another point E is connected to the, this is your piston, right? To the main piston, which actually controls the flow of steam to the turbine. This is your penstock, okay? And this valve actually controls the flow of steam to the turbine, okay? To turbine it is mentioned, right? This is the flow of steam. This is the valve, this is the main piston, and these are the auxiliary pistons, okay? And these auxiliary pistons in fact helps in passing the high pressure oil to the main piston for its control. Now how it will control, we'll see. Now I can see this is a flywheel mechanism which is connected to shaft, and it is actually rotates at the speed of shaft of the generator. And this point A is connected to the reference setting where we have some knob mechanism or something. When we make it, we can make this point A down or up as per our requirement. Okay. So now we'll see the operation. If suppose I want to change the reference setting, I want to increase the speed, then if I will down it, okay, point A, then what will happen as this point is constant, now your point C will move off and your point D also will move off, right? So as soon as this auxiliary piston will move up, then high pressure oil will pass through this, right? It will move off and it will pass through this, right? Okay. Now, when high pressure will pass through this, then your main piston will move down. And when it will move down, what will happen? Then your steam flow will increase to the turbine and the turbine speed will increase by that, right? And similarly, if we want to decrease the speed of the turbine using the reference setting, I should now move the knob in such a way that the point A should move off. So when the point A will move off, this is fixed. So therefore now as it will move up, your point C will go down, right? And as it will go down, point D will also go down. And hence your auxiliary piston also go down, right? As it goes down, then your high pressure oil will move through this. So as it will move through this, so it will now move off this main piston and simultaneously your valve will close towards the closing position, it will move, right? So as your valve will move towards the closing position, your steam input will gradually reduce and your turbine speed will decrease. So this is the process by which we can control through the reference setting. Now coming to how we can control through the through the speed, how it responds the change in speed. Let us see. So how it responds the change in the speed. So the change in speed can be responded by this first, because this is connected to the shaft. Now, as soon as this spring flywheel is connected to the shaft, as soon as the speed increases, the shaft speed increase. So what will happen then? Then these flywheels will actually move away from each other. So this will move away from each other in this direction and in this direction, right? So now what will happen? As it will move away, this point will go down, right? That means your point B will go down. This point is now fixed, right? Point A. Now as this point B will move down, point C also will move down, then point D also move down. So what will happen when point D will move down? Then your high pressure oil will pass through this, okay? Now your main piston will move off. Hence, what will happen? Your valve will now move towards the closing position and your steam turbine or steam flow will decrease, and hence your turbine speed will be decrease. So it is automatically adjusting. We can see here when the speed is increasing, it is automatically adjusting, the speed will decrease again. Again, when the speed will decrease, then the nominal speed or rated speed, what will happen? These flywheels will move closer to each other, right? So as it will move closer to each other, your point B will move upward. And this is a continuous phenomenon. We can see, right? As the point B will move upward, point C will also move upward, and hence point D also will move upward. As the point D will move upward, what will happen? The high pressure oil will move upward, and high pressure oil will pass through this, and hence your main piston will go down, and it will open more and more to pass the steam, high pressure steam, to the turbine, which will increase the speed of the turbine. Okay, so this is the mechanism of operation for a governor system. The mechanism remains same somehow. Because of the technological advancement, some components have been changed. It is made more automated, more responsive, right? So therefore, this is a classical approach shown, classical figure shown, but the approach remains same. Only the technology is changed and it is made more automated, right? Now we'll see the modeling of this governor system, turbine governor system, right? Now we'll see it. Now at point A, this position is related with reference setting, right? When point A is going down, that means your power is increasing, right? So we'll consider the moving down as positive and moving up as negative. So then if there is an incremental change in the position A, point A, that I can say delta YA, that will be directly proportional to delta P reference, which I can multiply proportionality constant Ka delta P reference, right? Now, coming to point B, if I'll consider incremental change, positive incremental change in B, point B, then your delta YB will be equal to Kv delta omega, right? So as your speed will increase, then this will also decrease, go down, and it will increase the power here, right? So therefore, delta YB is equal to Kv into delta omega by omega B. So in order to make it in power units, so I have written delta omega by omega base. Now coming to point C. If I'll see point C, so the incremental change in point C have different impact on point A and point B. Okay, so as the point A moves down here, what happens? Point C actually moves up, right? When point A moves up, point C moves down. So they are opposing to each other. So therefore, I can write delta YC This incremental change happens because of the opposing incremental change in A. So therefore I can write minus of Kca into delta Ya. And the impact of point B on point C, I can see it is proportional, right? It is not in reverse order. So therefore I can write plus of Kcb into delta Yb. Right, so delta Yc, I can write it is equal to minus Kca into delta Ya plus Kcb into delta Yb. Right. Now, coming to point D. So in point D, there is incremental change in the positive direction, delta Yd will be equal to Kdc delta Yc. Okay, because they are proportional directly. As the point C will move down, point D also move down, and as the point C moves up, point D also moves up. So therefore, delta Yd I can write Kdc delta Yc plus how it is related with point E. So when the point E moves down, your delta D also, point D also moves down. When point E moves up, point D also moves up. So therefore, it is directly proportional. So therefore, I can write KDC delta Yc plus KDE delta Y. Right? So these equations are clear now to you. Now, a change in the position of point D. This is little bit to understand. A change in the position of point D affects the position of point D through the time delay associated with the fluid in the servo here. Because you can see here, when there is a change in point D, suppose let us say point D position is going down. Now what will happen? So the high pressure oil will pass through this. Now it will go up, right? So point E is going up. That means your point E position is depending on point D in a reverse way, but with a time delay. And that time delay, we can mark it with a differential equation. So I can write it as with constant Ke. So I can write dy dt of delta Ye equal to minus Ke delta Yd. They are instantaneous. These equations are written based on the instantaneous response, right? But here, this equation I'm writing a differential equation because it is not instantaneous, some time delay is involved in it, right? So now this PSB, this valve power here is PSB here, sorry, this is the valve power. This PSB is directly proportional to the amount of steam passing through this channel, right? This is called valve power. And this valve power is directly proportional to delta E. So as the point E will move down, so your valve power will increase, and it will go off, your valve power will decrease. So therefore, your delta SB, delta PSB is directly proportional to delta YE, right? Now, just substituting delta YD here in this equation and delta YC in this equation, okay? And the whole equation of delta Y, after substituting delta YC here, I can substitute delta Yd in this equation. Now your equation, oh sorry, again we have to substitute delta Ya here, delta Yb here, right? Then again we'll substitute delta Yc here, then delta Yd here. Now substituting this, we'll get this equation. Now I can write TSB, sorry, I can write 1 by K into KD. Just after manipulation, I'll get this equation into KD by KDC, KCA, K into dy dt of delta Y. That is equal to delta P reference. This is delta P reference minus KCB by KCB into KB by KCA into K into delta omega by omega base minus KD by KDC KCA K into delta Y. So now this whole term I can write it as delta PSB, which is nothing but I can write it a constant term. Delta PSB I can write K or K into delta YE, right? Okay. So this K is nothing but this KD by KDC into KCA into K. So that is delta PSB, right? So similarly here, this is also delta PSB, right? You can write this as delta PSB. Okay. So now if I write this in the perfectly in equation form, the constants as constants and equation form, it will be become TSB. This term is your TSB, and this term will be your 1 by RD. This is your regulation. Okay. Then I can write TSB d by dt of delta PSB equal to delta P reference minus 1 by RD into delta omega by omega base minus delta PSB. So this is your final equation now. Okay. So this is the equation for your governor system. So now we have seen today the modeling of hydro turbine system and modeling of the steam turbine system, the modeling of the governor system. This turbine governor modeling is same for both hydro as well as both steam, because the fluid may change, but the equations will remain same. With some constants, they may change. This time constant TSP may change. 1 by RD may change, this regulation constant, or we can say droop coefficient may change, but the equation pattern will remain same. Okay, for this governor system, which is applicable for both hydro turbine as well as the steam turbine. Okay. Okay, so we'll stop here, and tomorrow we'll complete the half portion of your syllabus. Tomorrow we'll look at the load modeling of the load. Okay, so thank you very much for your kind attention.